Hello everyone, welcome to my black hole simulator. I'm going to tell you a little bit about what went into making this, and then I'm going to tell you a bit about what it is and what it's doing. So this is my capstone project for Seattle Central via RST. This has taken me 2 quarters to do, mainly because of the workload that I have taken on for that time. It is written in Java. We are using an Euler's method to predict the orbits themselves, and this was a lot of fun to build. I learned an awful lot about relativistic mechanics. I learned a lot about my limitations. I learned a lot about even how much my friends love me. It was pretty awesome. It was a great project. Anyway, enough with the boring stuff. Let us go to the perhaps even more boring stuff. If you look over in the bottom left-hand corner, you will see 4 formulas. The very first one is called the effective potential. This tells you basically your potential at any particular point, and this is dependent on your position, the size of the black hole, and the ratio L over m, which is your orbital momentum ratio. The one below that is the equation that will tell you how your distance from the black hole is changing with respect to your time, and that involves both the ratio E over m, which is your energy ratio, and the effective potential. The equation below that tells you how your angle changes as you get closer and closer to the black hole, and we usually set it as a theta of 0 along the positive x-axis. The very last one is called the Schwarzschild time-like metric. This metric is what describes space-time around the entire black hole, and that depends upon how far you are away from it and the mass of the black hole. Those 3 equations above it are derived from the Schwarzschild metric. It is a beautiful thing. Now, this metric applies to non-spinning, non-charged black holes. So if this black hole was spinning, that we would be using, I think it's called the Kerr metric. Charged black holes, I'm not too sure of at the moment. Anyway, so most of these orbits are dependent upon the effective potential, that very first equation. The key to that equation, though, is the ratio L over m. Quick word on that, L over m and E over m we're taking as ratios. Now what this seems to imply is that regardless of the mass of the object, if it's at that position and it has an energy ratio of, what's this one here, 0.988, and it has an L over m ratio of 3.75, it will follow that exact same trajectory mapped out. Oh, here's an excellent example of what I was actually wanting to show you. Now, there are certain points via L over m, which I just screwed up all my words, 1 second. There are certain points along the effective potential equation in which you can see it dips down a little bit before it comes back up. That area there is called a potential well. What ends up happening is if your energy falls in that area at that particular distance, this vertical axis here is your E over m, and the horizontal axis is your distance from the black hole in terms of the black hole radius. If you fall within that little divot there, you're going to get these spirograph orbits, one of which you can see going on right now. I have this set up to go, I believe, 10,000 iterations before it restarts. That way we're not stuck on this one for too long. Right. So there are a couple different orbits that can occur. 2 of which we are very probably not going to see. This one is a spirograph orbit. I call it that. I'm not quite sure what else to refer to it as. But that is if your energy is not at the minimum, nor does it go up to that maximum level there for that potential well. It falls somewhere in the middle. So as you're moving toward the black hole, the difference of your energy, if you look at the second equation, subtract the difference of the potential, will eventually become 0. At that point, your orbit turns around and it starts heading in the opposite direction, away from the black hole, until that difference again becomes 0. The other orbit that we have seen quite often is a plummeting orbit. That is where your energy is above that bump there, that maximum. So regardless of what goes on or where it starts, it will end up just plummeting in. There are a couple right there that you can see. The other two is if you get an energy that hits the minimum right there in that potential well. If you hit that minimum, that creates a stable circular orbit around the black hole. The other one is if your energy, as you move toward the black hole, hits the very tip of the potential energy function there. I'm sorry, the effective potential function. What will happen then is your object will come in and it will rotate around the black hole several times in what seems to be a circular orbit, and then it will plummet in. That's called a knife edge orbit because it's teetering on the very top of the effective potential function right there. And then eventually it will just plummet in. Alright, well, I'm going to get rid of that graph. It's a little There we go. So, to reiterate a little bit, because we deal with the ratios E over M and L over M, any object that has those ratios at that position will follow these trajectories. So it's gonna plummet. That was almost knife edge. That was really close. So this could be a mango, this could be an elephant, this could be your mom, this could be, well, maybe not another black hole. That would introduce some physics I'm not quite prepared to get into yet. But, you know, a satellite, any particular object, take your pick. What's also interesting is the size of the black hole itself does not matter either. As you scale the black hole up, if you scale out your viewing area, you will see these exact same orbits, just larger. So this is all set for a black hole of a Schwarzschild radius of 1. I'll explain what that is in a second. And I believe I have it to where every 10 pixels is a meter. And we are running at a 1/10 of a second scale. Right. Oh yeah, this is a massive one. This is near the top of that function there. Bring that up real quick. Yeah, that's looking to be about near that knife edge orbit that I was mentioning earlier. It's going to come down, it's going to do the same thing. It's beautiful. I have it set up though so it'll only go through so many iterations so we don't get bored on the exact same one forever. It might start slowing down too because of the way I have the little tracer set up. Oh yeah, I made a small mistake with those. That's okay, I see what I did. This way we're going to get the entire orbit though. Yeah, it looks like this one will just plummet in. So current goals for this thing at the moment are to bring it to 3D and to provide an interface of some sort in which you could at least move around and you know, gain different vantage points. Potentially something like the Universe Sandbox, except using relativistic physics. I am not sure if I ultimately want this program to stay in Java or if I want to jump into other languages. My top pick would be Python, because I really enjoy Python, though I haven't got to mess with the graphical capabilities of it too much, especially the 3D stuff. Additionally, I want to introduce other mathematical methods, such as Runge-Kutta of an arbitrary order. So maybe I can compare Runge-Kutta 1, which is Euler's, which is what's going on here, with Runge-Kutta 2, 3, 4, and 5, just to show them next to each other for anybody interested in the mathematical inaccuracies of running at a 1/10 of a second per iteration. Additionally, I would like to show the Newtonian equivalent if there is one. Now, there are some orbits that Newton says are physically impossible. And so they won't have, these particular orbits may not have a Newtonian equivalent. but it would be pretty interesting to see. With Newton, though, you get a lot of ellipses. They'll come in and they'll just form this oval with the black hole at one particular focal point, and just, round and around. Because of the nature of the programming, though, we're not deriving the orbit mathematically. We're using an approximation method, so you may end up seeing some can't remember what it's called, some rotation of the ellipse as it goes through, if I was to show the Newtonian approximations alongside this. Further research also involves introducing spinning black holes. What those do is they introduce frame dragging. As the black hole spins, it drags space-time around it. So while you're standing in a single position, space-time is moving underneath you, so you're not really standing still. And that metric, I'm sure, is pretty interesting to work with. Furthermore, we could introduce a charged black hole, which I'm not sure if I mentioned earlier or not. But a charged black hole also changes space-time and requires a different metric. So comparing those orbits to each other would be vastly interesting, as well as taking on more complex cases in which the mass of the black hole may indeed not scale linearly, like I mentioned. So I'm going to mute my mic because my computer is throwing a fit at the moment. Going to let this go for another little while longer till we get a nice another spirograph kind of orbit, and then we will leave it at that. Thank you so much. If you have any questions, leave them in the comments below, and I will get back to them as soon as I can. If there are any corrections that need to be made, please let me know as well. I am not officially a physicist yet, but I am certainly working on it. Alright, thank you. Have yourselves a great one, and I will see you later.